share my screen.
Good afternoon, everyone. Thank you for joining us. I'll just give it a minute to let people join the call, and then we'll get going.
Yeah, the one that always. Yeah, the one that always. Must be like two.
Okay, thank you very much for joining, everyone. This is one of the installments of the HEA's Hydrogen Bytes lunchtime sessions. Today we're joined by Lee Gardner from Hydroluminum, and yeah, we'll be very pleased to hear from Lee in a second. Lee will deliver around a 20-minute presentation about Hydroluminum and their technology, and then we'll have an opportunity for a short Q&A session at the end. So if you do have any questions that pop up throughout the session, please feel free to leave them in the Q&A section, which you can access on the toolbar at the top. But briefly before we kick off, I'd just like to say that this webinar series is brought to you by the Hydrogen Energy Association. We're a member association of around 100 members from all across the hydrogen value chain, from hydrogen production to hydrogen derivatives, legal and planning services, university members, as well as a whole range of members who support in the supply chain and manufacturing of components related to hydrogen technologies. So really pleased to showcase our members in these lunchtime sessions and give everyone an opportunity to get to know our members and their technologies. And without further ado, I'll pass over to Lee from Hydroluminum. Thanks, Lee.
Okay, thank you very much. Good afternoon, everybody. Let me start with the number 60. That's the number of major clean hydrogen projects that were cancelled globally last year. 60 projects with announcements, press releases, government backing in some cases, all gone. And here in the UK, a country with one of the world's most ambitious hydrogen strategies, just 11 projects were funded under our first hydrogen allocation round. 125 megawatts of capacity against a 10 gigawatt target for 2030. Now let me give you a different number, 9.1 million. That's the number of tons of aluminium waste that went unrecycled globally last year. Dross, swarf, powder, end-of-life scrap, multiple waste streams across multiple industries. And the UK's contribution? Last year alone, we exported over 600,000 tons of aluminium scrap, a 43% increase since 2016. Not recycled here because, simply put, it's not cost effective to do so. In fact, Make UK published a report just last week warning that soaring aluminium scrap exports now threaten our defence, clean energy and automotive supply chains. The material our critical industries needs is being shipped abroad. My name is Lee Gardner. I'm from Hydroluminum, and in the next 20 minutes, I'm going to show you that those two problems are connected and that the solution is both is sitting inside the other. Hydroluminum was formed by energy developers and researchers with one goal: to commercialise aluminium as a recyclable fuel and energy carrier. At the heart of what we do is our catalytic water system, CWS, patent protected and built to take multiple streams of waste aluminium and convert them into three high-value outputs: low-carbon hydrogen, aluminium hydroxide, and heat. We have our innovation centre in Newport, where we're actively testing the full ecosystem around the CWS. This includes aluminium pre-processing, hydroxide filtration, hydrogen compression, and end-use applications, including hydrogen internal combustion engines and fuel cells. Our R&D has been independently validated by Innovate UK through a smart grant of just under £500,000. We secured £2.17 million through the Borderland Inclusive Growth Deal towards full-scale deployment, and we're leading the consortium on a bid under Clean Maritime Demonstration Competition 7, Innovate UK's flagship Clean Maritime programme, with up to 121 million available. When public bodies allocate competitive funding at that level, they do serious due diligence. That backing matters. Before I explain how the CWS works, let me put the challenge in context, because for this audience, I think the scale of the UK hydrogen supply problem is worth a moment. The UK has set one of the most ambitious hydrogen targets in the world, 10 gigawatts by 2030. And let's be honest about where we are. HEA funded 11 projects, 125 megawatts in a year when 60 major projects were cancelled globally. The challenge isn't ambition, it's economics. Electrolysis, the dominant approach, has a structural problem. It has one revenue stream, hydrogen. That means every project lives or dies by the hydrogen price, the cost of renewables, and the availability of subsidy contracts. When any of those shifts, projects collapse. And there's a second problem. Even with dedicated renewables, you need electricity to drive your reaction. Your carbon intensity is tied to your power source. Your costs are tied to your energy costs. You are always exposed to the grid. So the question this industry needs to answer is there a production pathway that doesn't have those structural weaknesses? One with multiple revenue streams, no grid electricity requirement, a feedstock that costs a fraction of what renewables powered electrolysis costs to run. There is, and it's been sitting in the UK's industrial waste stream for decades. The catalytic water system, the CWS, is our answer to the problem I've just described. Let me start with what it produces. First, low carbon hydrogen, continuous on-site production, no grid electricity required. Second, aluminium hydroxide, or ALOH3, a high-value industrial chemical with significant global demand. I'll come back to why this is critical to the economics later. And third, thermal energy, 4.4 megawatt hours per tonne, delivered at 140 degrees Celsius, industrial grade heat, suitable for direct process use on site power generation or as an anchor supply source for a heat network. What goes in? Waste aluminium, drawn from multiple industrial waste streams, plus water, driven by our patented proprietary dual part catalyst. That's the IP that makes this work continuously at industrial scale. The reaction is exothermic. Once running, it's self-sustaining. No grid electricity, no external heat source, zero operational emissions at the point of production. 3 high-value outputs from a feedstock that the UK currently exports by the hundreds of thousands of tonnes every year. Each output requiring its own specialist technology to handle, compress, filter, and integrate. But that's a conversion I want to come back to. First, how green is the hydrogen this system produces? When you produce green hydrogen through electrolysis, your carbon intensity depends almost entirely on the electricity you use. Even when dedicated renewables, you carry manufacturing emissions from the electrolyzer, from the wind turbine or solar panel, you're still exposed to the grid at some point in the chain. Our pathway is structurally different. Our feedstocks is waste aluminium. Carbon cost of making that aluminium has already been assigned to the products it came from. The car part, the window frame, the drinks can, we don't inherit it. Our process is exothermic. We don't consume grid electricity to drive the reaction. The reaction drives itself. Zero operational emissions, no electricity draw, no fuel input once running. We are pursuing certification under the DESNZ low carbon hydrogen standard. We fully expect to qualify, and to qualify at a carbon intensity at the lower end of any production pathway currently available in the UK. Genuinely green hydrogen, not by virtue of the electricity tariff we buy, but by the fundamental chemistry and feedstock of what we do. Which brings me to the economics, because green credentials alone don't build projects. What makes this model uniquely viable is what happens to the other 2 outputs. I said earlier that electrolysis is one revenue stream, and that's a structural weakness that causes projects to collapse. We have 3. 1, hydrogen, same as everybody else. 2, aluminium hydroxide, or ALOH3, a high-value industrial chemical used in ceramics, pharmaceuticals, water treatment, and flame retardants. It's in demand globally, and here is the critical point. The UK imports the majority of its supply from Africa and Asia. We produce it domestically as a structural output of every tonne we process. We don't add it, it comes out of the chemistry. And number 3, thermal energy. 4.4 megawatt tonnes per hour, used on-site, converted to power, or sold to adjacent industrial users. What this means in practice is that the aluminium hydroxide revenue underwrites the hydrogen economics. We are not dependent on the hydrogen price hitting a certain threshold or for the project to stack up. The project stacks up on the chemicals revenue, the hydrogen and the heat are the additional upside. Now let me put some numbers on that, because I think they will land differently when you see them side by side. At current UK electricity prices, electrolysis costs approximately £19 per kilogram to produce hydrogen. That's just the electricity bill. Capital costs and maintenance are on top of that. For 1 tonne of aluminium, our system produces 112 kilograms of hydrogen and 2.89 tonnes of aluminium hydroxide. At our most conservative hydroxide price of £600 per tonne, co-product revenues cover all production costs. The hydrogen has an effective net cost of less than 0. Every kilogram we sell is pure additional revenue. At a premium hydroxide price of £1,200 per tonne, the co-products generate a surplus of nearly £16 for every kilogram of hydrogen before we sell a molecule of H2. £19 a kilogram for electrolysis, effectively zero net cost per hours. That is not an incremental improvement on the economics. That's a structurally different category of project. And those premiums are fully justified. But to understand why and why hydroxide is a fundamentally different product to anything the bioprocess can produce, I need to explain the feedstock. Aluminium holds more than twice the chemical energy per unit volume of diesel. That energy density is what drives our reaction, delivers the heat yield, and produces the hydrogen quantities I've described. Chemistry works because the feedstock is extraordinary. But the real differentiator is the aluminium hydroxide, because our AlOH3 is not the same product as a standard market supply, and I want to be precise about why. The Bayer process digests bauxite in hot sodium hydroxide, caustic soda. That means every ton of Bayer process AlOH3 carries residual sodium locked into its crystal structure. Not from poor manufacturing, it's inherent to the chemistry. That sodium is a serious problem across a wide range of industries, including pharmaceuticals. It restricts formulation for patients on sodium-controlled diets. In electronic ceramics and semiconductors, sodium ions migrate under electric fields and degrade insulation and dielectric performance, a critical failure mode. Sapphire production used in LEDs and aerospace optics, it demands costly additional purification. Water treatment chemicals, it ends up in the drinking supply. Our patented dual-part catalyst uses no sodium. Our AlOH3 is sodium-free, not because we added a purification step, but because our chemistry doesn't introduce sodium in the first place. For high purity and sensitive applications, this is not a marginal quality improvement, that is a categorically different product. And one final dimension, when aluminium hydroxide is heated between 1,000 and 1,300 degrees Celsius, it calcines into aluminium oxide, or Al2OH3, which is alumina, the fundamental building block for primary virgin aluminium production, fed directly into the Hydroluminum electrolysis cells that every smelter on the planet uses. From the 2.8 tonnes of AlOH3 our system produces per tonne of aluminium processed, we yield approximately 1.9 tonnes of potential alumina. We're producing a precursor to new aluminium, closing a loop that the global industry currently closes via a 130-year-old carbon-intensive process starting in bauxite mines of Guinea. The technology works, the co-product is strategically irreplaceable. Now, how do we deploy this? Our deployment model follows a simple but important insight. Aluminium travels well, hydrogen and heat do not. Electrolysis projects must be built next to their energy source, then face the challenge and cost of getting hydrogen to where it's needed. We flip the model. We locate the CWS where the heat and hydrogen are needed. Then we bring the aluminium to it, aggregated from multiple waste streams. Our target partners are industrial manufacturers, energy-intensive operations, and heat networks. On that last point, the UK government now has a heat network zoning regulations in force under the Energy Act 2023, with a target of heat networks meeting 20% of UK heat demand by 2050. The industry is actively seeking high-grade, reliable anchor heat sources to anchor new and expanding networks. Our CWS delivers heat at 140 degrees Celsius, exactly the temperature specification those networks need. That is the market actively looking for what we produce. Each project is structured as a special purpose vehicle, with a minority working interest for the partner. They commit to offtake, we commit to throughput, the incentives are completely aligned. At a Newport Innovation Centre, we are currently validating the full system ecosystem, aluminium pre-processing, hydrogen compression, end-use applications including hydrogen internal combustion engines, fuel cells, and hydroxide filtration and post-processing. Newport is where we prove the whole system works end-to-end. And Newport is also where we identified the right technology partners to sit alongside us in each part of that stack, because we know exactly what the CWS does, but the most effective commercial deployments will be built with the best compression, filtration, and integration specialists in the industry. That partner ecosystem is something we're actively building right now. Commercial pipeline is building, UK first, then Europe, and let me close by placing that in its wider policy context. We're simultaneously addressing 4 major government priorities: green hydrogen production, directly aligned with DESNZ's targets, and potentially the most cost-competitive domestic pathway available without subsidy dependency. Critical minerals, we onshore the production of aluminium hydroxide, a chemical currently sourced largely from Africa and Asia. Supply chain resilience, but directly into the chemistry. Circular economy, we take multiple aluminium waste streams currently exported from the UK and convert them into 2 high-value outputs, keeping that value here, not shipping it abroad, and industrial decarbonisation. Every site we deploy on gains a clean energy and chemicals capability built around material that was previously a cost or a misused opportunity. And that isn't just our assertion. Innovate UK have backed our R&D. The Borderlands Inclusive Growth Deal was committed 2.17 million to full-scale deployment, and we're leading the consortium on a bid under Clean Maritime Demonstration Competition 7, positioning our technology in one of the most active clean energy application markets in the UK right now. That is independent, competitive validation of both the technology and the commercial model. The technology works, the economics stack up, the policy alignment is there. The team is here, and the ecosystem around it, the compression, the filtration, the integration technology is ready to be built, but we'll come back to that. Kevin Gray, our founder and CEO, 30 plus years across finance, energy and technology, leading circular clean energy solutions. Douglas Olafson, our founder and director and COO, economics and finance background with a track record of structured deals, scale ventures across energy, sustainability and beyond. Martin Moore, our founder and chief scientific officer, 20 years in R&D and global hydrogen technology, co-director and founder of Ecolox, and recognised for his work in low energy nuclear reactions. John Anderson, our founder and chief technical officer, 8 years of chemical R&D focused on testing, optimization and scaling, and 20 years of prior experience of BP and Shell. Together, here's what we're doing. We're taking the hundreds of thousands of tons of aluminium waste that the UK exports every year and turning them into some of the greenest hydrogen on the planet, underpinned by the revenue from a critical industrial chemical that the UK currently imports from abroad. No subsidy dependency, no grid electricity requirement, no operational emissions. Just chemistry and the discipline to see the exported waste stream for what it really is, a domestic energy asset waiting to be unlocked. Before I hand over, one thing I want to say playing into this room, we are actively building the technology ecosystem around the CWS, compression, purification, filtration, thermal integration, end-use applications. The platform is real, the deployments are coming, and the right technology partners will be part of every one of them. That sounds like an opportunity for your company. I'm not talking about a business card and a follow-up email in 3 weeks. I'm in a real conversation today about what working together could look like. Come and have a word with me. Thank you very much. I'll be delighted to take your questions and take a breath for now.
Thank you. Thank you very much, Lee. Can you hear me okay? Or am I on mute still? Okay, great. Yeah, thank you. That was an excellent presentation, and there's so many different aspects of your business model and technology that's really fascinating. And at the HEA, we're really pleased to support a range of different production pathways, including more innovative pathways such as hydroluminums. So great to hear more about it in a lot of detail in your presentation. If anyone has any questions, feel free to pop them in the Q&A. And I suppose a question that I have to kick off with is the aspect of circular economy in terms of the using aluminium waste that's maybe available in the UK. My question is around how much of that is available in the UK itself, how much of the feedstock supply is a limiting factor for scale up, or is that more of an opportunity as you see it?
Yeah, it's more of an opportunity as we see it. As we currently said, there's around 600,000 tonnes like was exported last year. And basically that gets sent either to landfill abroad or it gets sent to Turkey or India, where they will process it and then sell it back to us at a premium. Our idea is to interrupt that. We've already spoken to the government about this. They're very keen for us to do that, disrupt it. We're talking about building a large pre-processing plant, potentially in the West Midlands. We've just started discussions on that now, where we will be processing hopefully around 10 tonnes an hour so that they can then be distributed around the country to the different CWS systems. That 10 tonnes an hour will make a big dent in what's getting exported already. And we believe that will be the starting point. We can probably get up to around 40 to 50 tonnes an hour before we would need to start really looking at maybe shipping aluminium in, but that's obviously a long way away. So it's not something we're too worried about at the moment. And there's enough waste streams out there, some of which carry gate fees. People actually pay to get rid of them. And as we get better at what we're doing, we can start taking more and more of these dirtier process streams. And yeah, that's where the opportunities really lie. That really becomes circular then.
Great. Yeah, good to hear about that. There's a question in the chat from Darren. He's asking, when would this technology go live? So I guess, could you maybe touch on your future aspirations for the next year or so?
Yeah, so currently we have our first of kind, which is currently being commissioned as we speak in Newport. That's basically going to be running. We've got a hydrogen internal combustion engine down, and as I said, we're putting the ecosystem around it. But in reality, it's up and running and working. This isn't R&D level anymore. This is about scale up now. We've currently got 5 commercial opportunities that we're evaluating at the moment. Definitely 2 of them will move forward by the end of the year. So yeah, it's all going to move pretty quickly. As I said in the presentation, I'll say it again. We're looking to work with other companies. We do what we do really well, but around the compression, the filtering, the other aspects of the hydrogen, we're very, very open to working with people and sort of taking them on that journey. And yeah, as I said, there's plenty of commercial opportunities for us out there. Well, we're chomping at the bit. We want to get this out there. We intend to be commercial by the end of the year.
Fantastic. And I guess on that vein, there's a comment from Andrew asking how people can contact you to discuss. So potentially, if you could leave your contact email in the chat, that would be a good starting point. But I'll let you comment on that.
Yeah, excellent. Yeah, yeah, I can see some coming through. What compressors do you currently use? Currently, we're not using any compressors. We come out of our CWS at around 3.5-4 bar. So we feed directly into a buffer then for flame arrestor, obviously. There's all safety procedures, but it's straight into a hydrogen internal combustion engine. Because we've got an R&D exemption at Newport, we can't sell our hydrogen until we go commercial, which, as I said, will be by the end of the year. So we literally create electricity on site with an internal combustion engine. But we are actively looking for compressors right now, so please reach out to me because they're very expensive things. So we're trying to get some quotes in at the moment and trying to bring our capex down.
Definitely. Great. There's a question from Benjamin in the chat who's asking about the technology readiness level that you see this process being at. So maybe you could touch on that, please.
I mean, honestly, I think we will probably validate to TRL9 within the next 4 to 6 weeks. We're probably technically at 7 at the moment, but we'll be at 9 within a matter of weeks. We're just basically doing the commissioning now.
That's great. Don't see any other questions currently, but if others do have questions, comments, perspectives, then really welcome them. I suppose another, maybe it's more of a comment than a question from me, is that in our kind of interactions that we have with UK government, there's often questions raised around the cost of hydrogen. So maybe you could touch a little bit further on your kind of 3 revenue streams and the different projects and products that you offer in terms of how that could reduce the cost of hydrogen and help the sector move forward in that way. Yeah, so as I said, the economics are basically underpinned by the aluminium hydroxide sales. So our feedstock is obviously aluminium, and I'm sure it's no surprise to everybody, the aluminium hydroxide is relevant. So the price of aluminium goes up, so does the price of aluminium hydroxide. So we're kind of price protected in that way. Then it's just about the quality of product and making sure you've got the right supply streams for that. We are the only, as far as we're aware, we're the only green producer of aluminium hydroxide on the planet. So that in itself carries a premium. And as I said before, with the current prices of aluminium, if we're achieving £600 a ton of aluminium hydroxide, then we're basically got a levelized cost of hydrogen of 0. So anything, if we slip slightly below that, then the economics of the heat and the hydrogen come into play. But ultimately, it's all about profit for us on the hydrogen, but it means we're not dictated to. So in reality, we want the price of hydrogen to come down because that makes us even more competitive. Fantastic. A question from Olivia at the HEA. Olivia asks, what are Hydroluminum's timelines to scale up? For example, private investment beyond the Innovate UK funding streams that you've already mentioned. Yeah. Okay, so I've got to be a little bit careful here what I say because we're under NDA with several people, but I think I can say we're fully funded to this point, to the first point of commercial. And then the way that we run this company is that every project is a ring-fenced SPV, and we raise money individually for each project. As I said, we've already got an Innovate UK grant
Scottish Borderlands grant for 2.17 million, which will match fund. So we're a £5 million project, roughly, will be one of the first ones in Scotland. We'll be breaking ground on that, potentially November, December time on that. And then there's a couple of others in the pipeline. As you can probably tell, I'm not an engineer. I've got a city background, and so have a couple of the guys here. So raising money is actually what we do. So it's one of the things that we do well. So yeah, we raise them individually into the SPVs, and that's how we fund that kind of thing. So we ring fence every project, and then the economics all stack up and make sense that way.
Really good to hear about all of those different aspects. Just checking to see if there's any further questions. Got about 4 more minutes, so if anyone does have any burning questions, then please feel free to put them in the chat.
Just wanted to just elaborate on Darren again. Darren's asking, what compressors do you currently use? As I said, currently we're not using any at the moment, but we are looking at a 2 ton an hour project in Scotland for next year that will be producing around 220 kilograms an hour of hydrogen. So we're very interested in talking to people about compression technology for that specific project. I'm getting quotes some crazy numbers at the moment. So if anyone wants to work with us on that and see if we can bring the cost down on that, I'd be very, very keen to have a chat. I'll put my email in the chat so everyone can pick up on that.
Fantastic. Yeah, hopefully lots of follow-up after this discussion today. And yeah, as with all of our Hydrogen Byte sessions, if anyone has any further questions for Lee after the session, we've left Lee's contact details in the chat, so you can contact him that way about this Hydrogen Byte session or any business opportunities. Fantastic. One final comment from Darren, worth a discussion with Proteum Green Hydrogen. Proteum are also a member of the HEA, so we can definitely put you in touch.
They work with a very good friend of ours, Professor John Maddy. So yeah, always open to speak to anyone that works with John.
Great. Okay, well, if there are no further questions, we will leave it there for today. Thank you very much, everyone, for joining the session today on a very hot day for many of us, I imagine. If you are a HEA member and interested in contributing to a future session, then get in touch with the team. And other than that, I'll say thank you very much to Lee from Hydroluminum, and have a good day, everyone.
Thank you very much. Goodbye, everyone.
Thank you.